Welcome to this lesson on efficiency, capacity, and discharge. This is Will White, and I will be your presenter. In this lesson, we are going to talk about battery efficiency. We'll review the differences between depth of discharge and state of charge in a little more detail. And we're going to talk about how different battery technologies rate the capacity of the battery. It varies based on the battery chemistry. When we talk about battery efficiency, there's a couple things that we need to consider. First, we need to know the difference between power and energy. Power, volts times amps equals watts, is the rate at which energy is consumed or generated, and it's instantaneous. Again, uses the measurement of watts, which is volts times amps. Energy is power over time. It's rated in watt hours, kilowatt hours, megawatt hours. We can look at efficiency using both power and energy. In general, efficiency equals the amount of power that we're getting out of the battery divided by the amount of power we put into the battery. So watts out divided by watts in. We can also measure it using energy, the amount of watt hours that we took out of the battery divided by the amount of watt hours we put into the battery. And some battery manufacturers even rate efficiency on amps. So it's the number of amps they get out of the battery versus the number of amps that they put into the battery. With lead acid and nickel iron batteries, their efficiency ranges somewhere about 80 to 90%. Nickel iron is actually a bit lower than 80%, somewhere in the 70-75% range. Lead acid can vary depending on the actual chemistry and the design of the battery. Lithium-ion battery efficiency ranges from around 90 to 98%, so quite a bit more efficient than a lead-acid battery and much more efficient than a nickel-iron battery. Let's take an example of battery efficiency using energy. In this case, we had some charging source, the utility grid, a PV array, a generator. It doesn't really matter what created the energy, but we have 100 watt hours that we're charging into our battery. If our battery is 90% efficient, that means that we're going to be able to draw 90 watt hours out of that battery to power our loads. If we divide 90 watt hours by 100 watt hours, we'll get 0.9, which is 90% efficient. If we only got 80 watt hours out of this battery, we would have an 80% efficient battery. The key here is that in order to get the same amount of watt hours out of this battery, if I wanted to get 90 watt hours out of a battery that was less efficient, say a 75% efficient nickel iron battery, I would have to generate more than 100 watt hours into the battery to get the same 90 watt hours out. We need to take efficiency into account when we're designing our systems because you're not going to get everything out of the battery that you put into it. This is a simplified example. It doesn't take into account losses for a couple different things, say AC to DC conversion if you're using a battery charger to charge from the grid. It doesn't take into account losses from a charge controller if you have a PV array charging the battery. It doesn't account for wire loss and other factors like that. So this is a simplified example. In the notes for this slide, there's an example using power. And power is really interesting because in the example in the notes, we use 10 amps going into the battery at 14 volts. Remember, amps times volts equals watts, so 10 times 14 is 140 watts. If we're discharging that battery, the same 10 amps coming out of the battery is going to discharge at a lower voltage, around 12 volts. So 10 times 12 is 120 watts. There we can see that there's an 85% efficiency there using power. Some battery manufacturers will only rate efficiency using amps. So in that example, 10 amps in, 10 amps out, that's 100% efficient, but it doesn't take voltage into consideration. And a lot of batteries voltage can vary significantly between the charging voltage, where the voltage of the array is higher than the voltage of the battery to push the current into the battery, versus discharge voltage, where the battery is pushing current out to a load, so the voltage is going to go down. As we saw in our example, the difference between 14 volts and 12 volts. That's going to affect the power. Amps times volts equals watts. So you're going to have lower power at the lower voltage. So we need to take that into consideration when we're calculating our efficiency. That's very important. So it's important to know, how is the battery manufacturer rating their efficiency? Are they doing it based on amps only? Are they doing it based on power? Are they doing it based on energy? It's going to make a difference, and we need to be able to make sure that we're comparing batteries using the same metrics. Let's review depth of discharge and state of charge and how they relate to each other. Depth of discharge, or DOD, is how much of the capacity of the battery has been used. That's what have I used out of the battery. State of charge, or SOC, is how much capacity is remaining in the battery. How full is the battery? Depth of discharge is usually used when designing our battery, and we usually talk about maximum depth of discharge. What is the most amount of the capacity of the battery that we want to use? And that's going to vary based on the battery chemistry and the manufacturer's recommendations. Lead acid batteries, we typically won't use more than 70% of the capacity of the battery, so we'd have 30% state of charge. Lithium ion batteries, we can use a much higher depth of discharge, typically somewhere between 80 to 100%. It's going to vary based on manufacturer's recommendations. The depth of discharge, or maximum depth of discharge, that you use from a battery is going to impact the lifespan of the battery, so we need to take that into account. We also have to remember that depth of discharge and state of charge are inversely proportional. So if we look at this chart here, 100% state of charge equals a 0% depth of discharge. We have 100% of the capacity of the battery available. We have used none of the capacity of the battery. If we have a 70% state of charge, that means we have 70% of the battery capacity remaining. We have used 30% of that battery capacity, 30% depth of discharge. If we go to a 30% state of charge, where we only have 30% of the capacity remaining, that means we've used 70% of the capacity of the battery, or a 70% depth of discharge. Let's talk about how battery capacity is rated. We see an example of two different lead acid batteries here. We have a T105 on the right and an L16 on the left. These are different size lead acid batteries. They're both 6-volt batteries, and they both have different capacities. Lead acid batteries are typically measured in amp hours. That's how we rate the capacity of a lead acid battery. And that capacity is rated at a C rate. C is the capacity of the battery at a specific hour rate. And how they determine that is they take a battery that is 100% charged, 100% state of charge, 0 depth of discharge, it's fully charged, and they discharge that battery over a period of time and calculate how many amp hours they were able to remove from the battery from 100% state of charge to a 0% state of charge, fully discharged over that time period. With lead acid batteries, the capacity of the battery is going to vary depending on how quickly the battery is discharged. If it is discharged over 20 hours, a C20 rate, in this example, the T105, we could get 225 amp hours out of that battery. If we discharge it at a lower rate over a longer period of time, a C100 rate, we could get 250 amp hours out of the battery, so an additional 25 amp hours. If we discharge that battery at an even higher rate, say a C5 rate over a 5-hour period of time, we would have a lower amp hour capacity of that battery. We can convert amp hours to watt hours by multiplying the amp hour capacity of the battery by the nominal voltage of the battery. In this case, at the 20-hour rate, the C20 rate, 225 amp hours times 6 volts, we get 1,350 watt hours, or 1.3 kilowatt hours. With lithium-ion batteries, because their capacity doesn't vary as much with the discharge rate, they're commonly rated in watt hours or kilowatt hours. Lithium-ion battery voltage doesn't vary much depending on how fast the battery is discharged, so I'm going to get approximately the same amount of energy out of the battery whether it's being discharged at a fast rate or a slow rate. The capacity of the battery tells us how long we're going to be able to supply energy to loads for. I'm going to use this number when I'm designing my system in order to calculate how long I can power those loads. Can I go for a couple hours, a couple days? It's going to vary depending on the capacity of the battery. Keep in mind also that we don't want to use the entire capacity of the battery in most cases because that will have a negative impact on the cycle life or the lifespan of the battery, especially when we're talking about lead acid batteries. Some lithium ion batteries can be discharged to 100% depth of discharge using the whole capacity of the battery. We're going to need to read the manufacturer's literature and see what kind of an impact that's going to have on the lifespan of the battery. Couple key points for this lesson. Efficiency is the difference between the amount of energy or power I put into the battery versus what I'm going to get out of the battery. I'm never going to get 100% of what I put into the battery out of that battery. The lower the efficiency, the more energy or power I'm going to have to put into that battery to get the same amount out. Depth of discharge and state of charge are inversely proportional, so they're opposites of each other. When I have a 100% state of charge, I have a 0% depth of discharge. When I have a 100% depth of discharge, I have a 0% state of charge. It's important to know the difference between those two. And finally, battery capacity is a rating of the amount of energy stored in the battery. It's either going to be rated in amp hours, which we commonly see with lead acid batteries, or watt hours, which we'll see more often with lithium ion batteries. And remember, we can always convert between the two by using the formula amps times volts equals watts, or in this case, amp hours times volts equals watt hours, or we can divide the watt hours by the nominal voltage of the battery and get the amp hours so we can compare different battery technologies. Thank you for joining me for this lesson. We'll see you next time. Have a great day.